Our second speaker is going to be Luciano De Sio, and he's from the University of Calabria in Italy. He's going to talk about Policryps structures and applications. Welcome.
Good afternoon. My name is Luciano De Sio, and I'm a postdoc in the University of Calabria, Italy. First of all, I would like to thank the organizers for this opportunity. In this presentation, I will talk about a new kind of holographic diffraction grating realized in composite material, which we have called Policryps. Policryps is an acronym for polymer, liquid crystal, polymer slides. So, the outline of this presentation is I will introduce a new active holographic setup, which is very useful in order to realize good morphology grating. Then I will show you the main optical and electro-optical properties of a Policryps grating, and then I will do an overview about the main application which have been done by using the Policryps morphology. You know, in order to realize a good holographic grating, it's very important to take into account the stability of the interference pattern. Mainly when we want to realize a grating with a very short pitch. What are the typical sources of noise? Typical sources are, for example, mirror fluctuation, mechanical instability, temperature variation, airflow, and so on. And in addition, during the Policryps realization, we have long curing time, and we have also high temperature during the curing process. This means it's very important to take into account the stability degree during the curing process. How it is possible to control the stability of the interference pattern? Our personal trick was to mount on the same metallic disc, which is also the holder of our sample, in the top of the curing grating, and in the bottom, separated by a few millimeters, a reflective test grating with the same French spacing of the curing grating. In this way, by using this reference grating, we can couple the reflective component of one beam with the diffractive component of the second beam, and by using this additional photodetector, we can monitorize this reference intensity. Just we can monitorize this reference intensity in real time. This is where we can calculate the phase between the curing grating and the interference pattern. What are the typical results? So, if the system is not stable, these are the typical fluctuations. But when we stabilize the system by increasing the mechanical stability, I mean by reinforcing all by cover the interferometric part with some magnetic box, we are able to reduce this kind of fluctuation. But you know, it's not very easy to work every day with this kind of bunker setup. In order to solve this problem, our personal approach was to use this reference signal in order to drive a piezo mirror connected feedback configuration in order to keep constant the interferometer phase in real time during the curing process. In order to realize this kind of optical feedback system, we start with a calibration of the piezo mirror itself in no loop configuration. Just by applying a ramp voltage on the piezo mirror, the voltage is increased along the blue curve and decreasing along the red curve. We can see a sinusoidal-like behavior of the reference intensity. And by using this simple formula, we can relate the number of the peak with the displacement of the piezo mirror. We can see the typical result. As we can see, the voltage is increasing along the lower curve and decreasing along the upper curve. As we can see, between these two curves there is an hysteresis area, and this hysteresis area is strongly related with this waiting time, where the waiting time is the time between two different applied voltage. So we can see there is a linear region where we can work in order to realize this kind of feedback action. If we will do a linear fit of this region, we can calculate also the displacement factor. We can see now what are the typical results by using this kind of PAD protocol. So if the feedback system is off, these are the typical fluctuations. As we can see, there is a long-term fluctuation due to probably some mechanical relaxation, and also fast jitter is present due to the local noise. But when we switch on our feedback system, the system is able to keep constant this phase, and the typical fluctuation are about 6-7 nanometers, and this is also the sensibility of our piezo mirror. So, just in order to test again our system, we introduce ourselves an external perturbation. As we can see, when we remove the perturbation, the system in few seconds is able to dump this kind of parasitic fluctuation. How it is possible to realize this Policryps grating? Just we start with an homogeneous mixture of monomer and liquid crystal. Then we increase the temperature, and we have the liquid crystal in isotropic phase, because just we have the temperature above the nematic isotropic transition. Then we start the curing process by sending a UV interference pattern. We have the polymerization process in the region with high intensity. And due to this polymerization process, and due to the high temperature during this process, we have a diffusion. This means the liquid crystal go in the region with low intensity, and the monomer go in the region with high intensity. Then we stop the curing process, and by using a very slow curing rate, it is possible to very well align the nematic liquid crystal, which is in the low intensity regions. You can see here a nice picture of a typical Policryps grating. They are composed by polymeric walls alternated with homogeneous, well-aligned nematic liquid crystal. What are the typical properties? High diffraction efficiency, short switching time, and low switching voltage. You know, diffraction efficiency is a function of several parameters, like the incident angle, birefringency, thickness, and so on. We can see the diffraction efficiency of a Policryps grating versus this parameter. For example, this is the behavior of diffraction efficiencies by varying the incident polar angle. As we can see, there is a very strong correlation between diffraction efficiency and the incident polar angle. We have almost 100% of diffraction efficiency at the Bragg angle. In the same way, we can also apply an external electric field, and we can just turn the liquid crystal, we can change the liquid crystal organization inside the bulk, and we can switch off our system with a very low voltage. Just we need to keep in mind that for the standard HPDLC, the typical switching voltage are about 20 volts for micron. In the same way, there is a very strong correlation between diffraction efficiency and the thickness. In order to do this kind of experiment, just we realize this wave cell. As we can see, by using two different wavelengths, it is possible to obtain, by varying the grating depth, 100% of diffraction efficiency, for example, for green wavelength. And then when we change the thickness, we can go versus to very low value of diffraction efficiency. The same thing we can do with the red wavelength. This means just we need to keep in mind that this very strong correlation between diffraction efficiency and the thickness of the cell. Okay, now I will do an overview about the main application which have been done by using this Policryps. One of the main applications has been to use the Policryps structures in order to turn the polarization light, the polarization of the light, just to use it like a phase modulator. So, just we can see here a sketch of the cell on the rotation stage, and this is just a typical optical microscope view of a Policryps grating. Just we put our cell into being cross or parallel polarized. We want to monitorize the transmitted intensity versus this rotation angle. So, in this case, it's very important to obtain a grating with a very low diffraction efficiency if we want to do a very good wavelength. This means, because we are analyzing here the transmitted intensity, we can see now that behavior of the transmitted intensity versus the incident angle. As we can see, the two curves have been down for two different configurations, I mean cross and parallel polarized, and there is no overlap in intensity. This is due to the sample, it doesn't solve this with the alpha wave plate condition. So, in this case, with the cross we have the measure, and the solid line is the fit. In order to do this fit, we have used the Jones metric formalism, and by using this parameter, it is possible to estimate the retardation. If we know also the thickness, we can also calculate the birefringency. As we can see, birefringency looks a little bit low. In general, we use a 7 liquid crystal. The typical birefringency is about 0.2. In this case, it's a little bit low. Probably it's due to the residual concentration of monomer inside the liquid crystal fringe. In the same way, we can put our cell at 45 degrees between cross-polarized. We can apply an external electric field and we can switch off our birefringency. This means that Policryps grating are good candidates to become achromatic switchable half wave plate. A second application has been done by using the Policryps for tunable optical filter. Just we use a single mode channel optical wave guide realized in glass. Then we put our grating on top of the light guide. If we send the light here in the input, due to the presence of the grating, there is some kind of break filter, and we have some kind of notch system. Just here we can see an optical microscope view of the grating on top of the light guide. So if we send, just here we have a sketch of our cell, in the input a broadband source in the telecom range, then we can see what is the typical output. As we can see, the signal is suppressed of about 20 dB at the break wavelength. In the same way, we can also monitorize the transmission spectrum, and the filter includes also coplanar electrons. If we apply a very low voltage, we can obtain the tuning of our system, and in this way, this kind of system is a tunable optical filter. So, the last application which has been done by using the Policryps morphology, the idea is to put inside a very low concentration of azobenzene liquid crystal. Just we realize our mixture with standard mixture, and just we had a very low concentration of azobenzene liquid crystal. Why we can't increase this concentration? If we take a look at the typical spectrum for the mixture, we have a very big absorption in the UV range. But unfortunately, this is also the wavelength which we use for curing the grating. If we increase this azobenzene liquid crystal, it is impossible to realize the grating. But new material which are sensitive in the green range, we are using now in order to overcome this problem. In order to test, in any case, this system, as we can see, we have a big absorption in the UV range, because the red one is the spectrum for the mixture. Instead, the blue one is the spectrum for the grating. As we can see, we have a good diffraction efficiency because we have a low transmission in the red regions. In order to test the structure, just we realize this all-optical setup, where just we use the red laser as a probe, and we use a violet laser as a probe. So we can see the typical result. We start with a diffraction efficiency of almost 85%. Then, when we switch on our violet laser, we have the transition of the azobenzene liquid crystal in the cheese configuration, and in this case we can switch off our system. Then we switch off our pump beam, and then as we can see a very slow relaxation. Why the system is slow? The system is slow because the concentration of azobenzene material is very low, and also because for this kind of preliminary experiment we didn't use a very well focalized spot beam, because our goal goal is just to test if the system works or not. So, in order to see if there is some correlation between the pump intensity and the switching time, just we perform this experiment by increasing the pump intensity. As we can see, there is a very strong correlation between the pump intensity and the switching time. This is because just the number of molecules which go in the cheese configuration are proportional to the impinging intensity. Okay, just some conclusion. We have seen this new kind of active control system, then also the property of a Policryps grating, and what is possible to do by using this Policryps chapter, like a switchable wave plate, a tunable filter, and all optical switch. Thanks for the attention.
Questions?
Have you been successful in forming reflection mode grating?
Yes, we are working in this direction. We want to perform this geometry in a reflection geometry. So probably the main problem is, imagine we have the liquid crystal homeotropic to the polymeric walls. If you imagine this condition in reflection, when you send the light, you see a uniform medium, because you see an ordinary index which is the same of the polymer. In order to see the grating, you need in this case to apply an energetic filter. So just we have the contrary situation.
You don't have random alignment in the ball.
We have this homotropic alignment. We have the this is for the surface. So surface no. I mean, imagine you have these polymeric walls, and we have the liquid crystal in homotropic alignment due to the polymeric walls. If you see this situation in reflection, probably it's the same, but we are working in this direction. I'm not sure about these results.
Questions? More questions?
You said that they were, this technology was useful for achromatic?
For?
You said they were good for achromatic devices?
Yeah, I mean for achromatic switchable wave plate.